Hi, I'm Mark Davis Marsh. I'm a systems engineer here at Texas Instruments. Today, I'm going to show you how to improve your component reliability through good thermal design. Let's get to it. First of all, let's talk about why I think you can improve your component reliability with good thermal design. When we think about lifetime, most people in our industry think of Svante Arrhenius, and he's a Swedish chemist, and he came up with an equation that basically breaks down to the speed at which a chemical reaction would happen. And what we in our field have done is we've come up with common values of activation energy for electromigration, silicon defects, and other types of failures. And what you do is you can plug that into his equation, and what you find is for every 10 degrees C that the temperature rises, you will see that you are twice as likely to get one of these defects, or you're twice as likely to get a failure. So basically, for every 10 degrees C rise, you're twice as likely for your component to fail. Now, this is compounded by the fact that for DC-DC converters, at higher temperatures, their efficiency drops. So at higher temperatures, they have more power dissipation than they would have had at a lower temperature. So you have the temperature rise due to your thermal design, and then the efficiency goes down on your DC-DC converter, which will cause the temperature to rise even more. So you need to be careful that you don't allow the thermal design to get too hot, and you'll actually get a hotter design than you expected with the decrease in efficiency. So the first thing you're going to look at for thermal design is your package. The smaller the package, the less likely you are to be able to get out the heat. Why? Well, if we look at these smaller packages, these mini SOs, the SOIC Narrows, they just don't have an exposed pad. There's no room for it in these smaller packages. And so then you have a wire bond which connects to the leads, and it's not a very efficient path for heat to travel. As we get to larger packages, the thermals start to improve, but it's not until we get to the packages with large exposed pads that we start to see improved thermal performance. So the large exposed pad is going to connect to your PC board. That's going to be the same as if you connected a heatsink to your package. So the larger your board that you're connecting, the more surface area. The surface area is what's going to dissipate the heat. So the more surface area you have, the better job you are at getting rid of the heat. And the exposed pad on the package is going to allow you to spread the heat onto the surface of the PC board. So let's take a look at a data sheet and go through all the sometimes confusing parameters on the data sheet and see how we can make sense of those to use in a thermal design. So here I've opened up the data sheet for the LM73605-06. These are 5 amp, 6 amp regulators. So there's a lot of power that's being used here, and these are a good example of when you would need a good thermal design. If we look at the pinout here, we can see that there's a large exposed pad. The large exposed pad is where you're going to connect to the PCB with thermal vias. The thermal vias are going to connect down to a ground plane. The ground plane is then going to spread the heat radially away from the part. What we've also done on this part is no connect pins here and here. And that allows you to pour a large amount of ground copper on the top of the PC board. That's going to allow you to spread the copper, spread the heat on the top copper of your PCB design. Spreading it on the top copper is more efficient than spreading it on an internal ground layer because then the heat doesn't have to transfer down into the board laterally and then back up. It can simply transfer laterally and then off the surface of the board. So now I'm going to discuss the thermal metrics that are often confusing. They're right in the electrical tables, but they're often used wrong or misinterpreted, so I'm just going to go over those quickly. The most likely one that's used incorrectly is R theta JC top. So R theta JC top is misused most often. It's the parameter that basically says that there's an impedance from the junction to the top of the case. So that's the JC top. And people misuse this because they think that they need to multiply this number by their total power dissipation in the IC in order to determine the temperature of the junction of their IC. And in reality, what this parameter is telling you is that you should multiply it by the percentage of heat that takes this path. The R theta numbers should be multiplied by the percentage of heat that takes that path versus a psi number, which would be multiplied by the full power dissipation of the IC. So in this case, we have R theta JC top. It's 14.6 degrees C watt per watt. And so that's telling you that if a watt of power took this path, you would get a 14.6 degrees C rise. And then we would use that to calculate our junction temperature. But like I was saying, most of the heat won't take that path, say 5%. So the surface of the IC is very small, and the surface of the PCB is quite large. And since heat wants to dissipate from the surface area, it's going to prefer to take off of the heat of the PC board versus the heat of the small IC, so perhaps only 5%. The number you should be using is psi JT. That can get multiplied by the total power dissipation, and it's already in its calculation determined how much of the power it expects to take this path. So from the junction to the top, JT, we can multiply its parameter times the full power dissipation of the device to estimate the junction temperature. And you can see that this number is only 0.1 degrees C per watt. So if you multiply that by 1 watt, you're only going to get a 0.1 degrees C rise. So you can see that the surface of the case is actually very close to the junction temperature of the device. And we use that all the time to determine how hot the device is getting. So if you're using a thermocouple to measure the temperature on the top case, or you're using an IR camera, the top case is a very good measurement of the junction temperature. You can kind of think it as like a Kelvin sense. The other number that's very useful for thermal design is R theta JC bottom. So that's the impedance from the junction to the bottom of the case. Just know that the smaller this number is, the easier it is to get heat out of the exposed pad, and that's going to make it easier for you to spread the heat on your device. Now, a question I get a lot is, how much PCB area do I need to heatsink the device? And what we've done in our data sheets and also on TI.com is we have graphs which will estimate how much PCB area you will need for a certain amount of power dissipation. So if we look on the data sheet, you can see that we have a curve of theta JA versus PCB area. And you can see that as the area increases, the impedance decreases, which translates to a lower temperature when you multiply that by the power dissipation. And if we look at what our PCB design on this demo board is, it's closer to 70 by 70 square millimeters for the amount of area that's given for copper. So you could predict that you'll get a R theta JA around 17 degrees C per watt. So what we're going to do is we're going to take an eval board, and I'm going to show you its how it's set up thermally, and then we're going to do some measurements with our IR camera. Here we have the EVM for the LM736OX series. We have the IC here, the inductor here, and what you want to look at is from the IC, this is going to be a point source for the power dissipation, and it's going to head radially away from the device. And anytime you make a break in that radial flow of heat, then what you're going to see is a hot spot. So later in the design, when I'm showing you the camera, we're going to see that this break in the design shows up as a hot spot. Now this break was specifically done for EMI and was a trade-off, but you can see that you're going to need to make trade-offs between EMI and thermals, and just know when you're making the trade-off. So here's our setup. We have a power supply that's running around 12 volts, and we have a load that's drawing 6 amps. Here's our IR camera. Here you can see the inductor, the input and output capacitors, and here's the LM736O6 IC. And you might be wondering why they're covered in a flat black paint. This improves the emissivity, and it really gives us a better thermal image. The demo board by itself has all sorts of shiny surfaces, and if you don't paint them with the flat black paint, those will actually show up as cold. And you don't want them to show up cold. You want to kind of get a real determination of the temperature of the board. So flat black paint, I actually like the ones that you would use to paint your barbecue. If we look here, so this is a close-up of the board with the orientation we were showing before. Here's the EVM under the thermal camera. Here's the IC, the LM73606. Here's the inductor, and you can vaguely see the input capacitors and the output capacitors. And you can see around the device the heat trying to spread radially as much as possible. Of course, due to layout constraints, there's components here which are blocking the thermals, but you can see the spread here where those no connect pins are. The spread is very good. Over here by the inductor, you can see there is a thermal break in that copper break that I was talking about before. And that copper break there is for EMI reasons, and you can see its effect on the thermals. Now, if we look at the temperature that the IR camera is reading, it's reading around 59, maybe 60 degrees C. We know that that's going to be very close to the junction temperature because the psi JT on this part was 0.1 degrees C per watt. So if we had about 2 watts of dissipation, you're off by about 0.2 degrees C. So we know we're very close to the junction temperature. So if we look at the 60 degrees C, and then we divide by the power dissipation that we can find on the datasheet for 12 volts to 3.3 volts at 400 kilohertz switching frequency, and then we find out that the power dissipation is around 2 watts. So we can back calculate, we can get an effective theta JA of around 17, maybe 17.5 degrees C per watt, and that's going to be very close to what we saw on our datasheet curve that showed us how much copper we're going to need to get to an effective theta JA. So you can use the datasheet to get an estimate of how much copper you need to get to the temperature that you desire. And now that you know that the psi JT number is the number to use to calculate your junction temperature, you can see that the case top at 60 degrees C is going to be very close, within half a degree of your junction temperature, so that you know that you're keeping the device temperature down. In summary, to improve the reliability of your design, you're going to want to take a look at thermals. So we've looked at package and how that improves thermals. We've looked at the different metrics that you can get off of the data sheet and how much board area you're going to need. We've also looked at the trade-offs on an EVM and how some trade-offs that might have been made for EMI can affect the thermals, and some techniques by having the cuts radially to the heat spreading and how that can improve your design. For more information, go to ti.com/dcdc thermals. Thank you for watching.